Okay, I just want to make a couple of notes before continuing with where we left off. So for the lab, those of you that have not gotten to the lab this week for Wednesday group, something I noted from Monday group is you need to come to the lab prepared in terms of all the calculations. So you have to read the lab addendum that is on Canvas, and you're going to do the pre-lab quiz, which has a lot of the calculations, but there are a couple of sections in the addendum that needs calculation. So this will make the lab go smoother if you come to the lab already prepared with the calculations. So please do that. And the other thing is lab notebook. I'll be checking lab notebooks on Wednesday. Please make sure that they are complete the way they need to be. So under week 1 and lab material, you'll find the first PowerPoint presentation we gave in the lab. And in it, there will be the components in your lab notebook. So please make sure you review that and complete your lab notebook by Wednesday. Okay, so here last time I had a calculation error myself. I had a decimal point that was off. So Ted was right when he did the calculation last time. So bring out that piece of paper you were working on, and I just want to quickly correct my mistake. Here it should be 2 zeros after the decimal. I had only 1 0. So 0.2 ml divided by 160 milligrams is in fact 0.00125 milliliter, which translates to 1.25 microliters. A very, very small volume, actually even worse than 12.5 microliters that I had originally. Because it's a very, very small volume, I really don't want to have decimal points for when you're taking out volume in microliters. So the best way to do that is to actually dilute 100 times. Last time I said 10 times because I had the 1 decimal point error. So it's really 100 times. I'm going to post this actually with the calculation on Canvas so that you have the correct calculations. But anyway, if we dilute 100 times, that means 0.1 milliliter in 10 ml. 10 ml is 100 times greater than 0.1. So the dilution would be taking 0.1 ml from the stock solution, the 160 milligrams per 1 ml, putting it up to 10 ml that by adding 9.9 milliliter DDW. So you in fact take 100 microliters and add it to 9.9 milliliter DDW. Then you end up with a diluted stock of 1.6 milligrams. Then you apply here the calculations to get 0.2, 0.3, and 0.5, as well as 0.1. So you apply the CV equals CV. All right? So that was my mistake from last time, a decimal point mistake. And again, I'll post that online as well. Okay, so we talked about buffers, and then we were trying to solve this. Anybody went through the calculation and came up with answers? Jacob, you have your hand up or no? Yeah, tell me what you found. So 0 point what milliliter? What did you get? Because I heard the correct answer somewhere. So anybody else attempted it? Grace. Yeah. Yes, you got that right. Do you want to explain it? No? Okay. I'll go through the calculations with you. So the first thing what you want to do, and this is an example calculation for something is in the addendum for lab as well. So I told you last time is you want to have a 1 molar concentration of a buffer. So that means the 1 molar is equal to a concentration of the conjugate base or the salt plus the concentration of the acid. The concentration of both should be equal 1 molar. So now we want to find the concentration of each individually. So we want to apply the Henderson-Hasselbalch equation. First of all, I need to get the pKa. I have the dissociation factor. pKa is negative log the dissociation factor. So pKa will be equal 4.76. You just use your calculator to get that number. And then you apply the equation of pH equal pKa plus log concentration of conjugate base over concentration of acid. So, and then you get, after you calculate, you get the ratio of A over HA, the concentration, is 0.69. That's by just doing the mathematical conversion of log. Then you substitute so that you're solving for one value. Let's say in this case we're solving for the conjugate base. So the conjugate base over 1 molar minus the concentration of conjugate base is actually the concentration of the acid. So by doing that, then we are solving only for conjugate base. In this case, you'll get 0.408 molar. And the acid is basically subtracting this from 1 molar. You get 0.592 molar. Any questions up to here? How we got those different concentrations? Okay. So in this case, what we're doing is we're determining how much in moles per liter do I need of the conjugate base and how much do I need of the acid. Okay, so now I have to prepare I want to find out how much I need to get me 0.408 molar. So to prepare 0.408 molar sodium acetate solution, we need this many grams. How did I come up with this value? So I start with number of moles. Number of moles equals mass over molecular weight. And molarity equals number of moles per volume. So number of moles equals 0.408. Clear to that? Okay. So molarity is 0.408. Number of moles is 0.408 moles. And then I have to solve for the mass, the amount that I need to give me this many moles. So the molecular weight, I gave you that, it's 82. So number of moles equals mass over molecular weight. So I'm solving for X. I get the 33.46 grams. So if I weigh 33.46 grams and put them in a liter, that will give me 0.408 molar sodium acetate. Questions? This is the time to ask questions if you're not certain how I got to this value. Okay. Now to prepare 0.592 molar, I have a 3 molar stock solution. So I apply X by V equals, well, I'm solving for X. X by the concentration times 100 ml by the concentration 1000 ml by the concentration I need at the end. I need 1 liter. So I'm preparing 1 liter, right? Preparing 1 liter. I'm making sure that I got that right. Okay, so the XML would be, after solving for X, 197 milliliter. So I need this many grams from sodium acetate and 197 milliliter of acetic acid. So the way to prepare my buffer is to weigh out 33.5 grams of sodium acetate in about portion of the water for 500 ml. You solubilize that, and then you transfer to a volumetric flask, add 197 milliliter of acetic acid solution, and then make up to 1 liter with DDW. Then I end up with 1 liter that has 0.408 moles of sodium acetate and 0.592 moles of acetic acid. That's one way of solving it. Any questions about that? Okay. Now, in the lab, you're going to prepare the buffer a little bit differently. And I think that way is simpler. So the way we did it in the lab, and that's the calculation you're going to make before you come to the lab on Wednesday. The way we did it is we prepared a 1 molar. In this case, you prepare the concentration of acetic acid and sodium acetate to the final concentration of your buffer. So you prepare 1 molar of acetic acid and 1 molar of acetate, sodium acetate. So you start with preparing the same concentration, final concentration you want in your buffer. So to prepare 1 molar of sodium acetate solution, we need to dissolve 82 grams in 1 liter of water. How did I get that? Anybody would like to tell me? I need 1 molar. So 1 mole per liter. So 1 mole equals mass over molecular weight. So I'm solving for X, and molecular weight is 82 grams per mole. So X will be 82 grams because it's 1 mole. So 82 over 82 is 1 mole. So I need 82 grams to dissolve in 1 liter of water. That will give me 1 molar sodium acetate. To prepare 1 molar acetic acid solution from 3 molar acetic acid stock solution, that means C by V equals C by V, and then solve for X, you get 33 or 333 milliliters. And then you make it up to 1 liter. So now you have a stock solution, 1 liter of sodium acetate and 1 liter of acetic acid that both are at 1 molar. So now how much of this I want to mix with how much of that? Then I'm solving for volume in this case. How many milliliters of sodium acetate do I need to add to how many milliliters of acetic acid solution to get to 1 liter of 1 molar concentration? So this is the way you're going to calculate it for the lab. But the lab, they ask you for 250 milliliters, so different volumes. So make sure you read that and calculate according to what's in there. 250 milliliters of 200 millimolar. So it's a little different concentrations and volumes. So here in your equation, instead of solving for a concentration in millimolar, you solve for volume, okay? Because you have equi-concentration. So here, you solve for volume. Your final volume is 1,000 ml. So you basically solving for A minus, and here instead of putting 1 molar, you're putting 1,000 milliliter in, because that's the total volume you want. So you get, for the conjugate base, you get 408 milliliter, and when you subtract it from 1,000, you get 592 milliliter. So basically you take 408 milliliter of sodium acetate and you mix it with 592 milliliter of acetic acid. You end up with 1 liter of 1 molar buffer at pH, whatever the pH was, 4.6. Okay, so 2 ways of solving it and 2 ways of preparing the buffer, and this is the way you're going to do it in the lab, but different volumes and different concentrations. Happy to repeat if anybody needs clarification. All right, so I expect everybody, especially the Wednesday lab group, to know this because you didn't ask any questions. All right, so that's it for buffers. Okay, so shifting gears back to chromatography. Okay, let's remember where we left off so that we can continue. What is supercritical fluid chromatography? Yeah, you can read about it. Anybody wants to volunteer? What's the mobile phase? Yes, example. Liquid CO2. How do we make CO2 liquid? Compress it. So we increase the pressure above the critical point. So that's why it's called supercritical. So CO2, liquid CO2, is used as a mobile phase. And stationary phase can be anything similar to HPLC. And the detectors similar to GC, and you'll learn about those when we talk about HPLC and GC later on. So it has several advantages because the fluid that we use is less viscous. So we reach equilibrium faster, elution is faster, resolution is better. And resolution is separation of the compounds on the column. What is reverse phase chromatography? What do we mean by reverse phase? Okay. Polar. That is correct. So in reverse phase, the only reason it's called reverse phase because it started off with the stationary phase being polar and the mobile phase nonpolar, and that was normal phase chromatography. And then when they said, oh, we can do it differently, we can make the stationary phase nonpolar and the mobile phase polar, then it became reverse phase. And it works better for separation of nonpolar compounds than normal phase. So in reverse phase paper chromatography, what type of compound travels the most with the mobile phase? So if I have reverse phase, would it be the polar or the nonpolar compound that would travel? The polar compound would travel most because your mobile phase is polar. The compound that is most polar would associate the least with your stationary phase and move more or fastest with their mobile phase. What does TLC stand for?
Thin layer chromatography.
Incorrect. What does TLC stand for?
Fair enough.
Okay. How does TLC differ from paper chromatography? How does it differ? Oh, Alex, go ahead. Exactly. So particle size in thin layer chromatography is more uniform and smaller. So we get more consistency from one run to the other, and we get better separation. Okay, what is the difference between isocratic and gradient elution? What's isocratic elution? Ted. Isocratic, we're not changing the concentration of the mobile phase throughout the elution. So we start out with 10% acetonitrile, we keep it 10% acetonitrile throughout. Ali, what about gradient? You change the concentration over time. You make a change in your elution. Whatever that change is, either gradually increasing the concentration or decreasing a certain concentration, or you are abruptly changing the mobile phase. Doesn't matter. As long as you make a change, it becomes labeled as gradient elution. What do we mean when we say increasing the strength of the mobile phase? Hold on. It's good. Let's see if anybody else. What does it mean, increasing the strength of the mobile phase? Okay, go for it.
If you have a stationary phase that is polar, and you want to strengthen the mobile phase, you make the phase more polar than your stationary phase. If your stationary phase is non-polar, you want to increase the strength of mobile phase. You make your mobile phase less polar.
Very good, excellent. Increasing the strength of the mobile phase, actually you gave pretty good examples, but meaning what we mean by increasing the strength is making the mobile phase stronger in a sense that the solute wants to interact with it more than the stationary phase. Okay, so that the solute leaves your stationary phase, doesn't stay connected or interacting, because you don't want your solute to stay on the column or on the stationary phase. You want it to come out. So in order to make it come out, your mobile phase needs to be stronger and compete with the stationary phase. So the example that Fan gave is, if you have a nonpolar stationary phase, you're starting with, let's say, water. But water is polar. So your nonpolar compounds interacted with the column. So in order for them to come out, you add an organic solvent to your mobile phase. You add acetonitrile or methanol. So you increase the organic concentration, organic solvent concentration over time, then your mobile phase become less polar, similar to the stationary phase, and it will then be able to get that solute off and move with the mobile phase. And the opposite is true. If you're starting with a polar stationary phase and then you want to increase the strength of the nonpolar mobile phase, you add water. So you decrease the percentage of organic and increase the percentage of water. So depending on what your stationary phase is, the way you change the mobile phase is different. It's not always in one direction. It's not always increasing the water or increasing the organic solvent concentration, or you'll see later we change the pH when it's ionic exchange chromatography. We change the pH, we change salt concentration. So changing the strength can be done in so many different ways. As long as you understand the concept of increasing the strength, then you will know how to change the mobile phase. Okay. Any questions? I would love for you guys to ask questions. You will make my day by asking questions. Okay. So last time we talked about adsorption chromatography, and we stopped here for partition chromatography. And partition, by definition, that means your solute is partitioning between two liquids. One of them is stationary and one of them is mobile. And elution of the solutes depends on the changing nature or changing the nature of the phases. So you can combine solvents or change the pH. Then you can speed up the elution or enhance the separation. When the most polar phase is held stationary, we talked about this is normal phase. And the opposite is true. When the least polar phase is held stationary, this is called reversed phase. And the only difference why one is normal and one is reversed is what started first. So in partition, the stationary phase can be a coated phase where the liquid is coated on a solid, or is bonded, chemically bonded. So the liquid, either you coat the silica with, or hydrate the silica, so the silica gel becomes, or the silica becomes a gel, and then the water becomes your stationary phase. Cellulose, also you can have a coat of water, and glass beads, the same. Bonded phase are usually better. Bonded support is usually better because you don't have to regenerate the column. So you don't have to always wet your stationary phase or make sure there is a good layer that is not stripped off. So the liquid is not stripped off. So bonding your liquid is always a good call or better use so that you don't have to regenerate the column, like I said. Common bonded support there are hydrocarbons. We talked about them last time. C8, C18, C30. And the longer the hydrocarbon is, the more hydrophobic you're making your stationary phase. So then the choice of using C8, C18, or C30 depends on the compounds you're using. You want to separate how hydrophobic these compounds are. You go with longer or shorter hydrocarbon. Another mode of separation is hydrophobic interaction chromatography. Hydrophobic interaction chromatography is under adsorption chromatography. It's part of adsorptive chromatography because in this case your solute is adsorbing, but it's adsorbing by hydrophobic interactions. So you tend to choose a stationary phase where your interactions or your hydrophobic interactions are formed but weak. You don't want them to be strong interactions, otherwise it would be so hard to get them out of the column. You would need really strong solvents to get them out of the column, and sometimes if you use strong solvents like alkaline, a high pH alkaline solvent to get those compounds out, or ethanol to get the compounds out, you might denature them, especially if it's used for proteins. So you might end up denaturing your proteins, and that is not a good thing, especially if you want to use those proteins for different analyses. So biomolecules adsorb to a weak hydrophobic surface at high salt concentration. So hydrophobic interaction chromatography is mainly done for proteins, okay? And then proteins have hydrophobic surface, but also have charge on the surface. In order for the protein to interact with the hydrophobic surface, you add salt, and the salt kind of mask the charges, so interact with the charges, and then the protein becomes hydrophobic and precipitate on the column. So the surface of the protein precipitate on the column. And the way to wash those proteins out is to remove your salt mobile phase and add water mobile phase, or gradually decrease the salt concentration. So if you start with 1 molar ammonium sulfate, you can either abruptly go from 1 molar ammonium sulfate to water and start washing off your proteins. But if you want to separate different proteins, you can gradually decrease the salt concentration. Go from 1 molar to 0.7 to 0.5 to 0.2 to 0. then you can separate your proteins based on their charge and hydrophobicity. Common support, hydrophilic support bonded to hydrophobic ligand is butyl separose. That's a common stationary phase that is used. So this is an illustration of what happens. Basically, the mechanism depends on salting out the protein. So you solubilize your protein in salt solution and you run a mobile phase that is salt solution. And then what happens at this case, you're at high salt solution, your proteins interact via hydrophobic interactions. At low salt, then you have charges, you reduce the hydrophobicity on the surface of the protein because of having charges, then they won't no longer interact and they would leave the column. The more hydrophobic the protein is, designated by more red area, less red, barely any red. So the more hydrophobic, it will interact the most and elute the last. The least hydrophobic will elute first. No one wants to ask anything? Okay. All right. I'm asking you now. Everybody will answer this question. Oh, come on. Hydrophobic. Who agrees with Sam? Okay. Caitlin, you disagree with Sam?
No, I agree. That was just like my answer on my
Okay. So yes, hydrophobic interaction, obviously. Okay. Moving on, ion exchange chromatography, and this is the most confusing chromatography for a lot of students because of the fact of how we name them. We name them anionic exchange, cation exchange chromatography. The way we name them will deceive the meaning. Are we separating positive charges or are we separating negative charges? So in this case, our solute or compounds of interest interact with the stationary phase via electrostatic interaction. So our solutes are charged. For the most part, they carry a charge. It's used, this type of chromatography is used, let's say, if I want to separate charged from not charged, that would be really easy. I can use, if I know that my compounds are positively charged, I can use cation exchange chromatography, separate all my positively charged compounds and everything else will not interact and will be separated. So I can use ion exchange chromatography to separate solutes that have different charges, okay? Different net charge. Some have plus 11, others have plus 5. I can separate them. They're both positive, but I can use cation exchange chromatography to separate those that are different in net charge. So often your stationary phase is a cross-linked polyelectrolyte, so that it's a polymer and carries an electrolyte, carries a charged group. Because you have to have a charged group for your charged solutes to interact with. So your polymers can be highly cross-linked. That will form pores that are small size pore. So you will be separating molecules that are of smaller molecular weight. So the more cross-linked they are, you are using those for small molecules. Lightly cross-linked, so they're not very much cross-linked, so you have large pore sizes, so they're used mainly to separate large molecules like proteins and nucleic acids. The small molecules like sugars, for example, or amino acids. this is one form of a polymer, polystyrene. That means you have a styrene with divinyl benzene. They form a polymer that is cross-chain polymer, and the R group here that you can see get derivatized, and then they will carry a compound or a molecule that has a charge. So if it's a positive charge, if the R carries a positive charge, then I am separating negatively charged ions. So this is called anion exchanger. So, and that's where the confusion comes. When you say anion exchanger, some students think, oh, the stationary phase is negatively charged. No, the stationary phase is positively charged. What is exchanging between the mobile phase and the stationary phase is the anion, because it's interacting with positively charged stationary phase. So we are exchanging anions. Hence, it's an anion exchanger carrying a positive charge. Opposite is true. Cation exchanger carrying a negative charge. So a cation exchanger is negatively charged, attracting positive ions. Polysaccharide base, which is most common, is you have a polymer from polysaccharides, and what happens here is the OH groups, one of the OH groups on the carbohydrate moiety is derivatized. That means a molecule is attached to it that is either weak acid or a weak base carrying a positive charge here, and the weak acid carrying a negative charge, an intermediate acid like the phosphate here, a very strong base, or a really strong acid. Okay, so the groups can be either weak acid, weak base, intermediate acid, strong base, strong acid. So when we say acid, then it's negatively charged. Base, then it's positively charged. So if you have an acid group on your stationary phase, would it be a cation exchanger or an anion exchanger? Please think about it, all of you. Go ahead, Zach. Yes, of course, I can repeat it. So if you have a weak acid as your stationary phase, would it be a cation exchanger or an anion exchanger? Anion exchanger. Any other? No, Ali. Why is it cation, Ali?
Because acid has a negative charge.
Yes. And the ion that will be exchanging is a positively charged ion. Right, Riley? Did you get that? Yeah. They hold on to protons and give protons, but when they give protons, they become negatively charged. Okay. So the selectivity of an ion exchange, that means how would they select ions, or how strongly these ions will interact with those stationary phases. It really depends on the ionic valence. What does it mean, ionic valence? Do you remember from your chemistry? When we say ionic valence. Zach?
Like how many valence electrons it has on its outer shell?
Right. That means how much charge it's carrying. Okay? So the more charge it's carrying, the more it's going to interact with the column. Okay? So, for example, I'm going to just draw by illustration here. So that is my column. It's negatively charged column. That's a minus here. And then I have an ion that carries 3 pluses, another ion carries 2, another ion carries 1, and another solute that is not charged. So basically the not charged is not going to interact with anything and is going to go with your mobile phase and elute first. And the one that is most charged will interact the most with your stationary phase, and then it will stay longer, and while it's moving, it's really hindered back by all these charges and interacting with these charges. Whereas the least charge will interact less and go first. So the valence here, this has the highest valence, this is the lowest, no valence. Radius, how big it is, the bigger, well, we'll learn in carbohydrate lecture, there is a combination of size exclusion and ion exchange chromatography, where you can separate on both size and charge. So the size becomes important because it will determine how well this molecule is going to go into the pore size and the pores and interact with your charged ions on the stationary phase. Concentration. The higher the concentration, we have to be careful. I think we talked about this last time maybe, is we cannot inject a sample that is very concentrated, because if it's high in concentration, then it will not have there will not be enough capacity on the column to interact with all of the molecules in your sample. So some of the molecules, even though that they're charged, they will not find room to interact and then will elute. So you have very poor separation. So concentration is really important to take into account when you inject a sample on your column. So the nature of the exchanger, we talked about strong acid and strong base and weak acid and weak base. So when you have a strong acid, that means it will remain dissociated no matter what the pH is. It will remain negatively charged. Even if you decrease the pH so much that you are giving a lot of protons, it's still going to be acidic. So it stays negatively charged at any pH above 2. Strong base is the opposite. It will remain positively charged even if you increase the pH above 7. It will still be positive unless the pH is greater than 10. So really in these cases, when you use strong acid or strong base, you cannot change the strength of the mobile phase by changing the pH. So this means you cannot change the selectivity of your stationary phase. When you have a weak cation exchanger, that means a weak acid, you can actually change the pH. You can increase the pH or decrease the pH, and then you're going to affect the protonation state of your stationary phase. By doing so, you are changing the capacity of the column. By changing the pH, you're changing how they are, if they're negative or positive. So let's say they are negatively charged at pH 6, and then you start decreasing the pH, that means you're adding protons, then they become, they lose their charge, they become protonated. So you lose capacity, you lose selectivity, sorry. And same with the weak anion, a base. So say you are increasing the pH, then you can deprotonate them. That means remove a proton from them, then they will lose their positive charge. In ion exchange chromatography, these two, the weak anion and the weak cation, are used a lot. Because often you have compounds or molecules that are similar in ionic strength, in ionic valence, and then you need to separate them. In order to separate them, you need to form a gradient. So you would change the pH to change the selectivity of the column, and you can separate them. In strong acid or strong base, you probably use them when you are separating compounds that are not close to each other. They are, maybe some of them are positively charged, some of them are negatively charged, so it's easy to separate them in one step. So, but if you have multiple compounds of different charges, like separating proteins, different charges, it's always better to use weak anion or weak cation, because you can change the pH. You play around with the strength of your mobile phase, then you are more in control of separation. So you change selectivity by changing the pH. You can also change the selectivity by changing the composition. You can add salt. If you increase salt concentration, for example, you are replacing the ions. So if you add NaCl, if you are exchanging anions, the Cl minus will replace the anions on the column, and therefore you can elute your compound. So the presence of salt is going to compete with your solutes, therefore you can enhance separation and reduce analysis time. In ion exchange chromatography, interactions between solute and stationary phase are mostly yes. Just to see who's here and who's not here. Affinity chromatography. And just to remind you guys, okay, there's a lot of information here, but throughout the semester we'll be giving examples of anion exchange, cation exchange, affinity chromatography, and so on. They will come back. Here we're just learning the principle. Later we'll learn application, and they will all, then everything will fall into place for you guys. Okay. So in affinity chromatography, we have a very specific interaction that happens between the solute and the stationary phase. Most of the time, it's very unique interactions. So if we have antibodies, that means we are separating specific proteins that have unique affinity to those antibodies. If we are separating enzymes, we're after a particular enzyme, then we will have enzyme inhibitors on the stationary phase that would interact specifically with our enzyme and separate them. So usually you have your support, which is inert. The support is porous, have high surface area material, nothing interact with nothing. That means it's inert, does not absorb anything or adsorb anything, such as agarose, dextran, cellulose, polyacrylamide, glass. And then you have a spacer here, and then your ligand. The ligand could be antibody, enzyme inhibitor, or lectin. Lectins are usually a type of protein that would selectively interact with glycoproteins. So then you have your analyte that will interact very specifically with your ligand, and then you need to separate them or have them elute from the column. So leaving the column, you either change the pH or ionic strength or temperature. By changing the pH or ionic strength or temperature, you're changing how these specific binding sites are. So you might change the charge in the binding site by changing the pH or changing the ionic strength. You impact how they're interacting with each other. Change the temperature, because sometimes you need a particular temperature for a compound to interact. So if you change temperature, pH, ionic strength, you change how they're going to find each other and interact. So that will make that solute leave. Sometimes you can have a biospecific elution method. Let's say you have lectins as your stationary phase ligand. You can add lectins to your mobile phase. Then now you have lectins in the mobile phase competing with lectins on the stationary phase, and that will make that compound leave. So what type of interactions? Anybody? All of them. Thank you, Alex. Yes, it can be any form of interaction that is specific between two compounds. So it can be hydrophobic, electrostatic, hydrogen bonding, or van der Waals. Okay, so we'll stop here. Yeah, you can turn in your